time could just slow down. This strange idea, which constitutes real-life time travel, seems impossible without understanding of classical mechanics. The foundation of classical mechanics comes from Newton's three laws of motion, which were developed and accepted centuries before Einstein first introduced his theory.
The theory of special relativity was developed and first published by Albert Einstein in 1905. Einstein had become highly interested in Maxwell's equations, which tell you that no matter how fast you are travelling towards or away from a source of light, the light wave will always travel at a constant speed of about 300,000 kilometers per second.
Einstein wanted to know that if he were to catch up to the light and travel at the same speed, would the light appear stationary? But that, of course, is not possible, as infinite energy would be required to accelerate something to the speed of light. Einstein began to think that if light has a finite speed, how will it be observed in different moving reference frames? He could only model this if the reference frames were inertial, in other words, objects in a state of uniform motion with respect to each other, such that using purely classical mechanics, we are unable to distinguish one from the other. The theory of special relativity relies on two assumptions known as postulates. 1. The speed of light in a vacuum is a constant, and therefore the same for all observers. 2. The laws of physics are the same in all inertial reference frames.
Using the first of these, we can justify some of the weird effects of special relativity, like time dilation. This is the phenomenon that time can tick at different rates depending on how you're moving. Consider two reference frames, the first being you stationary on Earth, the other a friend zooming past you in a train. You each have identical light clocks, where a beam of light is reflected between two mirrors. And when the light is bounced back and forth, you count one tick. As he is moving parallel to you, you see the light in his clock move in a diagonal motion. So you see the light in his clock travel a further distance, and as we know that the speed of light is a universal constant, and so must be the same for all observers, his ticks must take more time. So, from your reference frame, time ticks slower on his moving train. From his perspective, you are the one moving. Therefore, your clock must be the one running slower. As the two frames are inertial, and the laws of physics are the same in each, both frames are in fact correct in saying that the other clock is running slower. This helps set up the paradox.
6 years after Einstein first published his theory, physicist Paul Raghavan first presented the twin paradox, in which he considered the effects of taking journeys at speeds comparable with the speed of light.
Two twins, let's call them James and Angus, are standing on Earth. They are both 20 years old. Angus decides he wants to set off on a journey, taking a spaceship travelling at half the speed of light. After a while, Angus gets bored and returns home. When Angus gets home, he is shocked. Looking at James again, he realises he is aged differently. James is aged 30 years, while Angus is only aged 26. But how is that possible? We just saw that in each reference frame, the clock in the other frame appears to tick slower. So why and how do they both agree that Angus is younger?
Well, here's how. It's not as simple as before, so we can no longer say that from each twin's perspective, the other's clock runs slower and they are therefore younger. The big change occurs when Angus turns around to come home. When he turns around, his reference frame is no longer inertial, as he changes direction and therefore accelerates. Therefore, the theory of special relativity does not apply to the period of time when he is accelerating. Instead, we must use general relativity, which is a lot more complicated, but for this, we just need to know that general relativity states that accelerating clocks run slower. Because of this, the two twins both see the same thing and agree that Angus is younger by 4 years. So that's how to solve the famous twin paradox.
As we have seen, real-life time travel can exist, but unfortunately we will never be able to reap the rewards ourselves as we cannot travel near enough to the speed of light. The Concorde aircraft only managed top speeds of about 0.6 kilometers per second, which is tiny in comparison to the speed of light at 300,000 kilometers per second. So sadly, we can't just use this theory to slow the aging process.